Hi, welcome to Graph Power Hour. My name is Paco Nathan. I'm from Senzing, and I'm thrilled to be joined by my friend here, David Hughes from Enterprise Knowledge. And we've got a lot to cover this episode, but also want to understand your questions. We'll be covering some different technologies which are immediately applicable in this space of working with entity resolution, graph technologies, GraphRAG, and agentic workflows downstream. And so taking a look at that whole through line down there, from end to end, definitely, I think that there will be a lot of questions today, and I'll be fielding those in the Q&A section. But first off, I just wanted to introduce David and I have both been out at some conferences recently, and I've been thoroughly impressed, super enjoyed all the materials we've been presenting. We also have been working together on some projects, and I think that there's a lot to be said here today. We're going to cover a few different topics today, starting out with multimodal GraphRAG, talking about working with RAG augmented with knowledge graphs, but then looking across different modalities in terms of working with computer vision, working with audio, working with the semantic, the symbolic reasoning, if you will, side from graphs. How do these all pull together? And then from there, we're going to go and cover an amazing topic called BAML, something new from Boundary, where you have much more of a software engineering approach to working with large language models to be able to understand what is being extracted, say, from some unstructured content. And from there, we have a couple of the topics we're going to dig into as well, looking at higher dimensional associative reasoning and high dimensional computing as well. So without further ado, David, welcome. And I believe you have some slides too, so I'll let you get that queued up.
Sure. Well, thank you, Paco, for having me on the Graph Power Hour. It's great to be here. And yeah, let's just go ahead and jump into some slides. We'll try and get through a bunch of them, and please interject with questions, and we'll go from there. So I'm going to share my screen. All right. So hopefully everyone is seeing my screen. Is that correct?
Let's see here.
Paco, can you confirm?
Not just yet. Let me let's see what we got here.
I'm going to jump to, let me change that. There we go.
There we go.
Okay. Perfect. All right. Well, so what I'll tell you is this is an interesting image, and we all can come up with some ideas about what's in this image. You know, we see this dinosaur and he's holding a toothbrush. Is this just a fun thing that a kid put together? But there's a lot of information here that a language model will struggle with. And in fact, if you give this image to a language model, say a Google search, and you ask it to find similar images, it's really about where that model puts its attention. And you can see from the results that on to the right here, that a lot of the attention was actually on the scene composition of this being a sink. And in this image, these two images, you can see it actually paid some attention to the granite or the granite-like texture of the sink in the faucet's position, but it really missed I think the richness of this image. And this really is coming down to that dinosaur, the toothbrush in it. So what we're going to look at today is how do you include and incorporate the video aspects and also audio aspects into your GraphRAG application so that models have a much more comprehensive ability to respond and provide interpretability. And the end intent is to be able to ask an agentic system, find me, or I'm looking for images of bananas on a wooden table, and not only to get that Google-like result back, but to get the interpretability that here's 3 images. Yes, they have bananas in them, and there is a wooden table, but those outside images, this one and this one over here, are actually better And it's because they are either directly on the table that is also wooden, in that the dimensions of the bananas in these images take up the majority of the image. So these are pictures of bananas instead of the one in the middle where bananas are just a component. So these are some of the capabilities that you can get when you start to think about incorporation of images in a GraphRAG solution. When we first had this idea and I was scratching the back of my head of how I'd go about this, I thought of OpenAI's CLIP model, where you provide both an image, a caption, and then you can project that into a three-dimensional embedding space. And that three-dimensional embedding space looks something like what you see over here to the right, where if you select an image, you can find the other images that are similar to that. And that seemed pretty naive, but certainly impressive. But I wanted to go a little bit further. And so what we came up with was the ability to decompose an image into its component parts. Briefly, there's a lot of nuance here, but we not only looked at predominant colors in the overall image, textures, complexities based on the edges in the image, but we also then did segmentation and pulled out features like a toothbrush or the dinosaur and the faucet. Then when you do segmentation, for anyone who has done that, you'll know that you get a bounding box for each object that you pull out. And that bounding box has a center point. From there, you can do some interesting sort of spatial analytics. I can now start to say that this object, the dinosaur, is to the left of, or depending on your perspective, the right of the faucet. And you can start to do a small world network that resembles something like this rat's nest over here, of not only the yellow nodes being images, but that these are the objects in the image, and here's how they relate to each other. And we'll see here very shortly some additional information that you get. The overall thing that you accomplish, though, is that now you can create an agentic system that allows a user to query and look for similar images, and that not only do I get results back as a user that in fact are similar, but now because of the relationships and the properties on the nodes in this graph, I'm able to give back a richer understanding of why the images are similar, along with the explainability of that. So really quickly, we created this by ingesting lots of images from the Coco data set. We broke them down into their objects. We did a lot of properties on those objects. We also broke down predominant features, complexity of the image, and we also created a caption for any of the images that didn't have them. And we stored those in a embedding database, a vector database called LanceDB. That graph that you saw, and we'll see more details of here in just a second, we stored in a embedded graph database, and that is Kuzu. And then we used something called BAML to create an agentic interface that allows the user to query, find similar images, and then from the similar images, translate that into a graph query for understanding more of a global reasoning of the images that were returned from the similarity search in the vector database, and then providing all of that rich context, both local from the embedding database and global from a graph database, to a language model to then provide the kind of results that you saw. So I'll pause there, and if anyone has questions about maybe how we built this system or what some of the intent or capabilities are, please put them in the chat, and I'm sure that Paco will interrupt me and we'll go into those. But you saw that we used BAML. Very quickly, what is BAML? I think, Paco, have you had any experience, anyone using BAML?
Yes, certainly. This is, I think, one of my favorite developments to happen over the past probably like 3 years. Just seeing essentially a very structured software engineering approach.
Right, and that's exactly, I think, the highlight. If you walk away with nothing else from this portion of the talk about what is BAML, it's that it is a rigorous programmatic way of working with language models. Up until the point when BAML came onto the scene, it really was more a wild west of prompt engineers who behind the scenes really were prompt whisperers. And it was how good are you at begging a language model to give you structured output? Please, oh, please, my job depends on it. I really need this JSON. So what BAML did, and the team from Boundary ML, and hats off to Vaibhav and Aaron over there and everyone else, is that they came up with a DSL, a language, and it stands for basically a made-up language, but it's so much more than that. They came up with a DSL that takes the output from a language model, no matter what it is, and it aligns it into a type system, a schema that a developer creates for their use case. And what that looks like, and this may be hard to see, but please, anyone reach out to me later. I'm always happy to talk about BAML and any of the topics that we're covering today. But you, as a developer, can now create very functional types, add in some decorators called description, and you are giving your language models an understanding of what your expectation, this declarative statement of this is what I need back from the language models. And transitioning away from strings as our prompts to actually using prompts as functions. Here, we've defined that type that you saw just a second ago of I want some analysis to come back in a particular shape, but now I can programmatically work with my language model and provide not only what you're used to seeing, here's my request, this is just this regular string, but now I can go into and inject things like branching logic. I can do iteration. And right now this is using Jinja. Someday, very soon, we're looking at, the BAML team is going to be releasing capability to do other languages here. Probably TypeScript, I think, is in the queue, but the ability to now program your prompt versus relying on just the semantics you can create in strings. And then finally, your outputs from a language model are testable, not only in the development environment that you're working in, but actually even at runtime. That here we've called one of those BAML functions, and we get those back, and I can now start to go through checks and assertions that I've made, that I've said that my language model needs to give me something that has a certain length for this property, and I can now test that at runtime. So that's the highlight of BAML. There's really a lot more there, but I'm sure, Paco, you've probably seen a lot of teams struggling with working with language models and not being able to get the kind of deterministic outputs you can get with something like BAML.
Exactly. This has been the big question. How do you handle the unstructured side? We have some pretty good answers for how to handle the structured side of data, but how do you handle the volumes of unstructured data when typically there's like a 4-to-1 ratio? You have organizations that have so much more unstructured data. And it's been a big question mark. And this is actually a question that came up in Q&A too. Suraj was asking about key differences between some of these kinds of technologies. We hear about RAG, we hear about BAML. Where do these different pieces fit in together?
Great question. Right now, the place for something like BAML is when you are prototyping and you need fast iteration, where you can rely on discrete outputs from your interactions with language models, whether or not you're making calls to commercial models or you're making calls to local models that maybe you're running in something like Olama, but that you need the guarantee that the output from a language model is going to be discrete and that you are going to have it in a deterministic fashion. That is where you want to transition from using some of the other frameworks out there that don't give that kind of guarantee and really start thinking about your production step from your prototype step, that you don't want to have to switch mid-course. You should be prototyping in the same tool that you likely are going to use for production. There's some other tools out there that can guarantee structured outputs, typically from the model providers themselves, like OpenAI. The problem there is twofold. One, that is you're locked into just now the models offered by that particular provider. And then two, some of the ways that they make the guarantee that you're going to get a schema aren't quite what you would expect. Sometimes they will overachieve the deterministic concept of your outputs by really injecting in hallucinations or putting in information that the model is being forced to provide just so that they can guarantee that you're getting back your schema or your structured output. So it's generally a better concept to use a flexible tool like BAML, where you can use it across not only providers of language models, but also, enterprises have different teams working in different languages, and BAML is polyglot. You can use it if you are a Go developer, if you are using TypeScript, Python, or soon, and this is a nod to just the wonderful team at Boundary ML, is including things like Rust and or other languages. So having that flexibility, I think, is where the role for something like BAML to answer the user's question. GraphRAG, though, I think is to me at this point an easier question to answer, and that is localized associative search results from a vector database are only now what I think are one of the steps in a two-step process for how we search. And that is not only search for things that we are just trying to discover as users, but also search that we want to provide information to downstream agentic operations. I think that today's paradigm for search is a first step of associative search, and then taking the results of that associative, more cognitive, the way humans think about things, results, and then providing them to a more global, very deterministic search that is then performed in something in a graph, where you can use those results from your vector database result, and say you find 5 images of bananas that are similar. But now starting from those 5 banana images using their IDs, branching out into the world of your graph and looking at neighbors of neighbors, and different kinds of relationships, so that you can explore more comprehensively the area of the domain of your results. So I think that that's the new paradigm for search. It's not just associative search. It is also the bringing in the semantic layer and semantics and global capabilities of performing an additional step in a graph. What do you think, Paco? Does that answer that question from the user?
Yeah, certainly. Excellent answer there. I mean, it's probably also fair to say that BAML is really talking more about what you're drawing from sources, as opposed to RAG being more, like I say, as a portion of the search. Would there be cases of using BAML on the other end? Like, for instance, now I'm trying to think of a good way to express this. You and I have talked a lot about how we could leverage BAML when we're ingesting a lot of documents. But once we're producing a system, maybe that's using multiple phases, but like GraphRAG and then workflows downstream, can we be using BAML on, say, the end results to guarantee that a collection of agents are producing something that we would expect?
Yes, and in 2 ways, I think. One, lately I've been doing a lot of work with thinking about, or at least re-engineering, how I build agents. And lately I tend to lean towards frameworks from like Google, which is ADK, and wanting to inject deterministic outputs. So I found ways to use BAML in an agent that was developed in the ADK framework. So very excited about that. But to your point, I also think that there's a role for not only GraphRAG and what we'll look at for audio video, but also for BAML in doing ER. And I know that you and I have had some conversations about this, and I'm excited for our next one. But how do you enrich ER operations using audio and video and deterministic outputs from systems like BAML or frameworks like BAML? I think that will propel us into yet another capability of overall how we work with language models, how we remove and or reduce ambiguity in entities, and how we continue to evolve that ecosystem of creating knowledge.
Fantastic.
Well, so I did promise I'd look at this schema just a little bit more. As you can see, it is a rat's nest, but in the concept that when you do an associative search in your embedding database and you only get back a top K of, let's say, 5, 10 results, even though this looks very complex, it does actually narrow down to a very manageable set of data for a language model to reason across this small world network of spatial analytics, for example, the right of, the left of, that this banana is to the left of that cup and is above that, that desk. But some of the additional detail that you didn't see in those images are in those schemas is that, for example, on the image node, you can see the kind of things that you can start to capture to enhance a reasoning from a language model, the reasoning capability of an image. And not only can you put those kind of properties on the nodes in your schema, like this color is blue, but even on this relationship of uses color, you can start to have properties like predominance, how blue or how much blue is used in this image. And for example, the object, let's say this is a banana and this is an instance of a banana. And we know the spatial analytics of that banana to other image objects in the image. But on that contains relationship, we can also have that measure of predominance. Was this a picture of the banana because it took up the majority of the dimensions of the image? Or was it just a picture that had a banana in it because the bounding box in the banana was only a small portion of the overall dimensions of your image? So there's a lot of richness you can get from bringing in visual context in enriching your graph understanding of a particular domain. And that, that might seem still somewhat abstract. So let's look at some use cases here. This is an intelligence use case. Here we're looking at a picture of some ships, and we want to start to be able to understand concepts like, which direction are these ships going? What kind of ships are they? What are we not seeing in this image, but maybe we could hear? So let's see if this works. And you can tell me if this comes through, Paco. Are you getting some audio?
Definitely. Hearing that helicopters.
Right. So, like that
sounds like multiple.
Yeah, and so that's the thing. In this image, now we're going to talk about audio. We can't see helicopters in this image. And I can tell you there actually is a helicopter in this image, but it's very tiny. However, if we start to bring in audio, we start to be able to do some interesting things. One, we can do off-scene segmentation. So what was heard in the picture, but not seen in the picture. And unintuitively, you can also start to do an injection of temporality. Because we have stereo analytics, we have measures of loudness, we have some things called ITD and IAD. We can actually start to look at which direction was that sound going, and was it approaching us or leaving us? And so there's an interesting set of things you can do. And in fact, using BAML, using an agentic system developed with different language models, this is the information. Here on the left, you can read what was the description from the person taking the photo. And then here is the information we were able to get by bringing in both the visual, the audio, and putting that into a graph, and then using that in an agentic system to better understand these were the items that were found. And here is the belief of direction that this sound was going from for the helicopter, and also the reasoning. Why is that? So there, audio I find just as a fascinating new capability in this approach. Likewise, here's an image of a street corner, and we're going to listen just for a second to this one as well. And I won't play them all, but we can tell that this is a sound of police cars. Several went by us, and they were off picture. Now, if we were using video, you could do this in a stepwise fashion across keyframes in the video. But what happens if someone was just snapped a picture and was also recording the audio? And, so there's different use cases between video and static pictures here. But for this image, we were able to do that same kind of visual segmentation. You find the sort of objects you would expect, but now we were able to also analyze the audio, and we heard not only that there were some kind of police cars or emergency vehicles going, but we can count them because of that Doppler shift. And not only can we count them, but because of the stereo analytics, we could tell they were coming from the right of the observer of this picture and going to the left. And then, of course, here is just, you've probably heard of emergent capabilities with language models before. This is one of the newer discoveries of emergent capabilities, and that is the eerie capability of language models to now do geolocation of images. This one wasn't so amazing because, well, there was a street sign in the image, but I've given the newer language models an image of some cows in a field, and because of the structure of the irrigation ditches, the types of cows, and off in the horizon, the shape and structure and architecture of the barn, it was able to now start to make a reasonable guess that, oh, this is a picture of some cows in the Netherlands. And then the reasoning being is based on the architecture, the way that the berms and irrigation are structured, and the kind of cows in this image. This is likely where this was, and it's most likely this particular part of the Netherlands because they specialize in growing these kind of cows, are raising these kind of cows. So there's this emerging capability for doing geolocation of images in some very fascinating ways.
Oh, this is fantastic. And a question too here. Let me put it into Q&A. There we go.
Sure. Right. Let me switch over so I can see that.
Oh yeah, good question. So I guess, so I'll read off. Could this be used in the reverse? Does the audio actually come from this video or picture? Or, I mean, would be a way of inferring that there's some type of or fraudulent, data put together?
Yeah, I think that that's very true. It's a good use case. For example, car insurance. Hello, I don't know what's a good car insurance company these days. AAA. I'm at a car scene and my car just got into a wreck and I need to report X. Well, when being asked to also, can you take some pictures of the scene that you're at right now? You can start to listen and do audio segmentation from not just the dialogue occurring between the insurance agent and the caller, person reporting the accident, but listening in the background. Are you hearing birds? Are you hearing an amusement park? Are you hearing different kinds of objects? And then relating that to what is being presented in the pictures. I do think that just that first blush kind of concept, I think that that would be some interesting things to explore for doing validation of images to audio, and then to your point, audio to images.
Fantastic. Well, this opens up so much more. I mean, and it's probably fair to say that in addition to the LLMs doing reasoning, there's also a lot of capabilities across the graph to be doing reasoning, or to be doing some sort of analysis, pathing, centrality, etc. Techniques that we can use on graphs to leverage what we've got now.
Absolutely. And even to some of the conversations you and I are having, Paco, around entity resolution. Imagine that my image is of series of people. And these are images where maybe I have name tag or a bag, or I'm presenting something. You can now start to do or think about doing the segmentation of objects and the things like name badges on an object or the text that's associated with them, and start to pull those features out and use those in entity resolution. For example, is this picture of David Hughes at the Knowledge Graph Conference in New York? And so we have this metadata. Now we have several other pictures of me doing whatever else with enough metadata. And now there's some new images of me, and starting to use these features to determine whether or not this new image is David Hughes or is it someone else. So I think that they're using both audio, because even my audio has a signature. I talk with a certain cadence. I talk with a certain pattern. Maybe I typically pause here and there. I don't use a lot of ums, whatever. There is a signature to my audio. There is a signature to my physical features. And there's a signature to certain cues, if I were wearing a name badge, for example, that we can then extract and use further down the road into new inputs for entity resolution. So I'm excited about that capability as well.
Fantastic.
All right, let's see, is there any other questions before we move on to another topic?
And while questions come in, Suzanne, this would be a good time to put up another poll too. Poll is active.
All right, let's see our next poll. You're someone, Bradley, you wrote that human geoguessers are pretty good. Absolutely. There was a paper that just came out, maybe I can look that up and we can put it out in the notes later, where it's looking at the capabilities of human geoguessers, and now some of this emergent geoguessing capability from language models, they're getting closer. And of course, their ability to do it at scale, and the kind of latency that can be overcome, that I think is going to be really interesting. If you think back to that picture, even of those ships, maybe you didn't catch it in the description, but based on the structure and direction of the wakes from the ships, it was able to talk about direction. It gave us an understanding of what kind of ships. If you start adding in a few more things like what day of the year was the image taken, and we know the weather at that location as well, or even if you don't know the actual location, but you know what day it was, you can start to look at shadows of where the sun was, and then likely referencing maybe what part of the globe this was located in. So you can actually start making some reasonable narrowing of geolocation just based on subtle features in an image.
And we've discussed before, but that image of that battle group, those ships out at sea, that capability can be used, for instance, in illegal fishing, because a typical problem in illegal fishing is, even though the ships have transponders, they may run with their transponders off for a period. They may change a digit on the transponder. You can use entity resolution actually on vessels with transponder codes. But the problem being is that when people are trying to do bad stuff, they typically try to hide. And if you have some imagery and you can make inference out of that imagery, and then you can combine that with what you're able to resolve off of codes, transponders, and then tie it all together into a graph, now you have a chance of reconstructing a complete picture of what's going on.
And to your point, I know that there's some interest in if there's also some accompanying audio, say maybe from buoys in areas where pirates are working, or where fishing typically occurs, you can also start to think about adding into that entity resolution the signatures of boat motors. Motors have signatures as well. So all sorts of interesting capabilities there. Okay, let's see. We have a new question, it looks like, and before we jump into something else.
Yes, Hugo, I can read this out. Kind words from Hugo. Also, it seems like in terms of AI innovation, just above the saturation point at the boundary, we'd love to hear your thoughts about using these strategies to uncover, that is, infer perceptions and unknown intents of users, especially through AI approaches. Interesting. So Understanding about the intents in this kind of graph. I mean, uh, I'll take I'll make an attempt to try to interpret this a bit. And Hugo, please fire back if we're going off track here. But David, you mentioned the sense of using a small world. So in that sense, we've got a graph. It's maybe not large. It's maybe 20 or 30 nodes, something that is human scale to perceive. And within that world, we can start to infer at some point maybe some causality or some intention of some actors within that world. I'm always thinking about fraud and like looking at attack graphs and trying to understand, okay, what's the vector that came in, what are they trying to get? But of course, this can be used in many different ways, not just fraud hunting.
I think that that's a good point. You think about the results of an associative search being the subgraph from a larger graph. You can either work with just those results directly, or you can project them ephemerally into something like Kuzu and create a small world network in just an ephemeral database. But once you have that and you have other features like the audio and the video, you can start to analyze what are the physics of the small world represented in the image as well. And that's projected into your graph. And then even in audio, there's some things that are more subtle that you can start to try and think about intent as well. I may be explaining to someone that let's say, creating this new program has been hard. And these are some of the challenges I've had. When in fact, I could say it a different way. I could say, some of these problems have been really hard and it's been difficult coming over, So it's all about the tone, the emotionality can be analyzed as well. And I think all of those are features when you could start to think about inference over time. You'd want some larger sampling, I think, of either supervised or semi-supervised data that says that these kinds of features are associated with maybe this intent. But I also think back to the causality in thinking about causal graphs. There's some interesting work evolving from YHow and other tools out there, PyWise, for doing causality through graphs. And I think that enriching those graphs with things like images and features like audio, it's only going to enhance the capability of causality.
And it's probably good to mention too that this type of approach, combining these types of technologies, leveraging these kinds of capabilities now, it's not just a one-way street. I mean, we're working with agents, we're working with a lot of advanced technology. We're building up a graph as an asset, but there's also people who are domain experts who are in the equation. So I can imagine that once, you've got that subgraph and a threat analyst or, an intelligence analyst is looking at that particular scene, trying to understand what's going on, they might have some input that will really tip the scales for downstream reasoning about what's happening.
That's exactly right, Paco. And that's where I think that systems today are, I think, best positioned when the foot forward of having a human in the loop and providing that reinforcement learning with human feedback is critical. Agents, I don't see them as 100% autonomous. I see them as just a counterpart, a colleague to an entire ecosystem in the domain of intelligence anyway, that includes other types of analytic systems. It includes humans, and then it includes lots of validation. But I don't think that agents, I don't think that the capabilities we're talking about today are silver bullets. They are just another tool in the ecosystem in the domain.
Yeah, it is.
All right, well, maybe this is a good time to, we've talked about what are some of the use cases. I think that we just covered many of these, but what are the future directions for work like this? So one future direction we'll see here is got to thinking about, okay, we decomposed images into objects and we decomposed them into features like complexity, textures, predominant colors. But could you decompose an image any further? And if you did, what would you do with it? So I'll play this one more time, and maybe we'll just pause it here. And what I realized earlier in working with another group is images can be decomposed to one thing lower, and that is pixels. And well, what do you do with pixels if you decompose an image into pixels? And in the at least the medical domain, but I'm now thinking across other domains as well. In the medical domain, you get imaging from things like MRIs, certain kinds of CTs that the pixels aren't two-dimensional, they actually are three-dimensional, and they call them voxels. But if you think about any particular three-dimensional pixel, it's got three inherent relationships. It has an X neighbor, a Y neighbor, and a Z neighbor. And once you think about the pixels having neighbors and you then project those in through three-dimensional space, there's a fourth parameter that comes with those pixels in this kind of imaging, and that's intensity. How bright was this pixel? Now with intensity, I can start to do community detection and analytics, and I can say, aha, now I'm looking at a tumor, a lesion, and that can be in a brain, it could be in some other organ. But I now also have metadata that says this community is adjacent to this particular neuroanatomical structure in this use case. And before you know it, you have a brain graph. And this is a graph representation of an organ. And as medical images do, there's a series of studies over time that I can now compare that graph, that brain graph, and start to ask questions like, is this lesion spreading? Is it splitting? Is it condensing? So I can look at disease progression. As a corollary, I can also ask questions about what is the treatment response for this particular person and or presentation clinical. And so it was interesting to go through this, and I'll just finish playing this out and think about, oh yeah, pixels within a given use case, they're really just nodes in a graph. As long as you have some metadata to it, you can make some interesting leaps of thinking about what are some novel ways to apply graph, and this was one of them. So this is one direction I think where we'll see some continued evolution of where graphs can be applicable in novel domains and in novel ways, not just bringing in audio and video into graphs, but now just starting to think about ways of looking at other kinds of visual data or imaging data in this case. What do you think, Paco? Is it time to maybe wrap it up with the concept of what is hyperdimensional computing?
Most certainly. Well, I mean, let's go into this and also see, because I think this is going to prompt a lot of discussion, pulling the pieces together.
Okay.
Actually,
so
one thing that I'll interrupt, David. There was a question here I was going to answer in chat, but I think we put it up on the screen because I think this one is and this is a really key point. And Bradley was asking about how we can use these tools together across distributed systems, distributed sources, piecing together some kind of related analysis from multiple sources. And I was going to add an answer, but I'd love to hear your perspective on this. I mean, typically the analysts are working in case management tools. And so the immediate goal is you've got some facts in front of you. Is this a thing? Is this a potential fraud? Is this a potential excellent customer that you're looking at in your hospitality system? And if it's a thing, does it need to be escalated? Can you document what's going on in this case so they can be handled correctly? And so, my first pass on this would be, we're working with LLMs. One of the things that LLMs are really good at is summarization. And you look at tools like Perplexity.com, they're really good at effectively summarizing from multiple sources, generating a report. And so now we're kind of at that point where an analyst wants to look at a lot of different sources and come up with a report. So it just seems like a natural fit there.
Yeah, I think that I agree with everything that you just said, Paco. And I think the world is changing so rapidly that we're getting some interesting tools. And the one that I think that addresses this question very well is something from Google called A2A, which is a protocol for how agents will talk to each other. And I do think about federated intelligence, more so. It's a lot of where the work I do these days is in. And you can imagine an agent that an analyst is working with as their counterpart. And this agent needs to go and discover information about a particular event, but it's in different data systems that have their own set of entitlements, and need to be able to be restrictive about that information. So what A2A does is it sets up a couple of capabilities. And if you haven't looked at the A2A protocol, it's rapidly evolving, but it's going to be very formative in how we operate agentically in the future. So the scenario would be is that this agent then has, using the A2A protocol, the capability to go and discover other agents who can be given tasks specific to this question in this particular event. And they can then use the tools that they have. They can contact other local agents within their institution. Let's say one of them is where the credit card fraud. This agent may be a member of a team working at a particular bank and be asked, are there any events that have occurred for this user and their ID? It's been through entity resolution. That agent is able to accumulate that information. It can provide and apply the entitlements of maybe either obfuscation or redaction for information that it's not allowed to provide back out. I think that's where having systems like a unified entitlement service, something that EK is thinking a lot about these days, of then that agent being able to provide back secure but sensitive information, and then holding back what it can't reply back to the user who asked this question. And that is something that can be performed across many agents and across many different institutions until the requesting client agent has enough information to then provide an analysis and a synopsis. So I do think that the capability for federated search, federated intelligence, and some of these other federated questions, we're now entering into the realm where we can do that using protocols like A2A. Yep, there you go, A2A, Paco. That's their logo. All right, so we'll round off with hyperdimensional computing. It's a personal interest of mine. I do have a website on it, but it is very novice at the moment. I need to dedicate some more time to it, hyperdimensionalcomputing.ai. But what is hyperdimensional computing anyway? So let's briefly go over about 6 slides and we'll get into the high level of what is HDC. First, HDC, as the name implies, is using vectors that are higher dimensional. You know, typically you get something like 1,036 dimensions out of most embedding systems coming out of OpenAI. That clip model we use to make this projection that you see here, I believe it's 523 dimensions. But really the entry point into hyperdimensional computing, that floor, is around 10,000 dimensions. And once you get 10,000 or more dimensions, some interesting things happen. One is for any randomly created hypervector, just create a random vector, you get something called near orthogonality, which means that you can guarantee that the information incorporated in 2 vectors randomly created are nearly orthogonal semantically to each other. And that's really critical. And you'll see why in a second. 2, an algebra starts to emerge. And you get some operations or operators that are going to be very interesting to think about. Lastly, you get something called holographic distribution of information. And this isn't kind of the holograph from something like Star Trek. What it is it says that if you have 10,000 dimensions that represent some piece of information, that each dimension holds some portion of that information, and across all of those dimensions, it's replicated it to some degree, such that in most cases, between like 40 to 50% of that hypervector, you could have corrupted, have errors, flipping of numbers, and still retain high quality representation of the concept. So pretty interesting stuff. And my hypothesis is that we can use the concepts and features of hyperdimensional computing to think about graphs. And here's how. So real quick, hyperdimensional computing, like I said, we're going to start off at 10,000 dimensions. And one of the canonical examples is the following. Let's say we wanted to represent different kinds of shapes and colors. And the first thing we would do is create a hypervector, 10,000 dimensions, for the concept of shape, for the one of color. And truly, I just mean giving the word color, randomly creating a hypervector and assigning or mapping it to the word color. Now, ultimately, we'll talk about how to do that semantically using graph projections of lower dimensions, like things like BERT, up into higher dimensions, like a 10,000 dimensional space. But for now, you can just create a random hypervector for the word color, for shape, for circle, square, blue, and red. So now we have 6 randomly created hypervectors that are mapped to these words. Now, we can do the first operation you get in hyperdimensional computing called binding. It's effectively multiplication. Now we can say we can multiply the hypervector mapped to the word shape times the hypervector mapped to the word circle. And we're going to get back a single hypervector that represents and captures and encodes that concept of shape is circle. And the same is going to be true for a single hypervector for color, one for red. We multiply them and we get back a single hypervector for the word or the concept that color is red. Okay, so that's binding, first operation of 3. Okay, that's interesting, but what do you do with that? Bundling. You get a second operation, which is a superpositioning of those hypervectors, and then you add them, collapse them, and now we can take the single hypervector for the concept of shape is circle, and the single one for color is red. We can superposition or add them, and we get a new single hypervector, but now we've encoded the concept of red circle because we had shape is circle, color is red, superposition them, and now in a single vector, hypervector, we have that red circle. So to me, having these kinds of operations, I found just really exciting. And this was about a year ago. And then started thinking about, well, what was that? Graph applications, of course, because, well, this is where I've spent the majority of my life in the last more than a decade. And so I started to think about, okay, if we took a node of type person and we created some key value pairs like name, David, job title, architect, some skills, AI, etc., I'm going to be able to create those hypervectors using that multiplication for the key value pairs. I'm going to be able to collapse them using that addition operation of bundling, and I'm going to get back a single hypervector that represents all of these things about David, me. Then I'm going to be able to create a hypervector for the word nodes. And we can talk about this in some other presentation about how you do that and capture the semantics across embedding spaces, but you can do it. Then lastly, another hypervector for all the richness of who is Paco. And we can multiply those all together. And we're going to get back a single hypervector that represents a triple for those of us in RDF world. And I'm a big fan of LPGs too. There's a place for both. That we're going to get back a triple representation of an observation of knowledge. And that is David knows Paco. And additionally, we're going to then start being able to layer in context in our knowledge, something that current systems don't do. David knows Paco down here in the left-hand corner, but we happen to be talking during the graph power hour, which more is a concept. I can add that to my understanding of this observation. And now I can say, David knows Paco, given the fact that we are discussing or doing something in this graph power hour. Now, Paco and I go further back than today, but you get the concept. And then lastly, these things can start to allow us to do the following. Here we know the idea of inverting relationships allows us to retrieve information from a graph traversal. I can create a hypervector for the concept of David, the nose. And so what I get back is a hypervector called David knows. And I can go and do a search for throughout my embedding space, my graph now is just a big embedding space. And I can do it very performantly because these are just hypervectors and doing matrix applications and cosine similarity. And I'm going to find all of the hypervectors that are similar that incorporate concepts like David knows. There's a lot of things David knows, but it's going to bring back all of those because at least a portion of that triple is the David and the knows hypervectors. I can then find the David knows Paco relationship, the David knows Ben relationship, and I can invert the operations that we just looked at, and I can retrieve back or subtract away the David knows from David knows Paco, and subtract away David knows from David knows Ben. And lo and behold, I will actually get back the nodes by virtue of the fact that I have them as metadata in my embedding space. I will get back the nodes for who in fact does David know. And you can do this all the way out through things like friends of a friend, or I'm looking for people that David knows that work for EK or that work for Senzing or understand entity resolution. And there's a lot that can be done there. And then finally, there's something called permutation, and that allows you to capture and keep track of the sequence of events using hypervectors as well. But that's a whirlwind tour of all things hypervector and hyperdimensional computing. We could probably have another show just on Paco.
Oh, fantastic. So to try to tie a few things together, if you were doing multimodal GraphRAG, it seems like we could be looking at a variety of different sources and coming up with a lot of different attribution for them. And this would fit in very well with hyperdimensional computing because now, like you're saying, color, shape, etc. For any given individual, you might have a lot of different attributes, but we can work geometrically to understand how these attributes map then more generalized into concepts.
Yeah. And in fact, starting to build primitive system in using Rust for hyperdimensional operations, starting to explore just how fast or far you can take the concept of a graph application, but in hyperdimensional space. And I think, much like I said at the beginning of the conversation, it's going to be a two-step process. You want to be able to perform cognitive associative search in a hyperdimensional space that has semantic robustness. With the results from that, you then want to do what humans do every day. We're not databases. We don't remember everything. I mean, if that were the case, I'd be in trouble. I have trouble. But what I am good at is I'm good at associating and finding similarity of things. And then once I find some concepts through similarity and association, I can then go and do a query into a database and get the discrete deterministic output and information that I want. So that's where I think systems like hyperdimensional computing graph spaces are a companion to a more robust solution for search, intelligence, and many other use cases.
Fantastic. So going beyond the vector database and nearest neighbor search, now we've got operators, a kind of calculus, if you will, for doing a graph-based search and pulling in. This is fantastic. There have been questions that are popping up, and I think that in particular, what would be typical failure modes we could project on these kinds of technologies? Like if we're working with hyperdimensional computing, where would there be, for instance, some kind of false positive coming in?
Several, I think, and this is where there's some interesting edges to still explore. First, how do you perform search? Search is going to have to be akin to or similar, in my mind anyway, to how you create the hypervectors in the first place. So it's likely going to be more visual in the sense that these are my available classes. I'm going to pick a class. These are my available properties in that class. I'm going to fill out the ones that I think I know or I'm interested in knowing more about. These are relationships. And so I'm going to modularly compose my query almost visually, and then having the hypervector created from that and doing the search. If you're doing projections from a semantic space like BERT, then coming up with, and I've got some interesting ones that seem to be performing well, but projecting those up into a hyperdimensional space in a lossless or a less lossy way is going to be, I think, more work to be evaluated. The dimensionality of 10,000 dimensional space gives you a large breadth of opportunity to explore, but there likely will be some edges that I think that we'll have to think through around how many concepts can you embed in there and still expect to get reasonable results. Lastly, and there's more, but just lastly at the top of mind is if you think about the graph as just being a collection of triples, then semantically, if you're searching for sub portions of a triple, there's opportunity for collision, I think, there as well. If you ask for the top k, let's say k equals 10 of similar results, there's a lot of space of what is similar, and 10 being such a narrow number. I think that we're going to have to think about re-rankers in an intelligent way to ensure that the re-ranker is optimizing your results based on the intent of the query. So it's almost like the query is going to have to be decomposed to understand that we're looking for people who know someone else related to a company. And even though that may also be similar to people who have similar interest in skills and hobbies, you have to understand the intent to be able to re-rank the results, because at the end of the day, you're doing a similarity search. And as we know from the world of RAG and GraphRAG, without re-rankers, you can end up dropping and missing a lot of data and on your results.
And probably a useful generalization would be that if you are looking at your data and thinking about moving toward an ontology for organizing your data from multiple sources, there's a lot of room for being able to have relatively late findings, not having all of your semantic tagging immediately up front, but waiting until you see evidence collected from multiple sources before you make this kind of determinations. So this is one way of understanding, going back to our previous episode with Mike Dillinger and talking about relation resolution, as he was saying. If you are developing your ontology, here's the support you're developing toward. You kind of have to meet them in the middle at some point. But this is a much better way than just sort of arbitrarily ad hoc trying to tie everything into an ontology before you even start assembling the evidence.
Yeah, and so I'm excited to find like minds who are interested in this concept, and I think that there's much to be explored. But I do have some belief that this will complement where we are going with agents, associative search, and better being able to model what is a fuzzy world.
Yeah.
All right.
Fantastic. One last question, David. Where can people reach you? What's the best place? We had the link for hyperdimensionalcomputing.ai earlier.
That's a great place if you're interested in hyperdimensional computing. Otherwise, you can find me at dhughes@enterprise-knowledge.com. We can probably get that posted up here as well. And certainly, if you're thinking about projects in multimodal GraphRAG, you want to incorporate audio or video in your efforts, and or you're really thinking about how do we accelerate and enhance our teams in getting deterministic outputs from our work in language models, Enterprise Knowledge, myself, we are very eager to talk to you about that and would love to have and explore a conversation with you.
Wonderful. Thank you very much, David. This has been fantastic.
My pleasure. And thank you so much for having me.